Hello, my name is Tony Lentz with FCT Solder, and this is Fill the Void 6, a study of the impact of solder alloy on voiding in solder joints. This was originally presented in 2023 at SMTAI International. Here's the outline for this presentation. We'll have a brief introduction on voiding in solder joints and how that might relate to reliability. Talk about the root causes that contribute to voiding. And then I'll give a brief overview of prior work that we've done on this. I'll discuss the experiment that we set up to measure how solder alloy impacts voiding. And then we'll go over the results. We'll discuss solder paste refill performance in general, and then we'll correlate that to the voiding results that I found. I'll go over the conclusions that we can draw from this, and then make some recommendations on how to use this to minimize voiding. And then if you have any questions, please email me or call our main phone number, and we'd be happy to talk about this with you. So voiding in solder joints can definitely have an impact on reliability for certain applications. If you had a lot of voiding in BGAs like this on a sensitive component, it may cause RF problems or other signal transmission issues. Overheating is a potential concern, especially for BTCs. If the voiding is pretty large like this, that may interfere with the ability of that solder to wick heat out of the component. And then if you have a really exceptionally large voids or voids that are concentrated on a plane, either at the board pad or at the component interface, then that can lead to cracking in the solder joint over time as the device is used. With that being said, Hillman and his co-authors found no correlation between voiding and reliability for QFNs tested with 4 different solder alloys. That paper was published at SMTAI International 2019. But I have heard from customers that voiding can be related to reliability for some applications. We deal with LED manufacturers, and in some cases, voiding does lead to overheating failures, and they have potential product returns because of that. And I've heard from a monitoring and measuring device manufacturer that voiding in their solder joints led to some signal noise that interfered with the ability of the instrument to do the precise measurements that were required. So in some cases, voiding can be related to reliability. Here are common industry limits for voiding. So in J Standard 001 and IPC A610, 30% max area is allowed in BGAs. 50% max area is allowed on QFN thermal pads. In the 7093 standard for bottom terminated components, they don't actually give a limit. Instead, they just report that less than 30% area is typical on thermal pads. But then they refer to J Standard 001 for the actual limit. And then in the IPC 7095 standard, which covers BGAs, for class 1 and 2 products, the limits are less than 25% area or less than 50% diameter in a solder joint. And then less than 20% area and less than 45% diameter for class 3 products. Regardless of what these limits say in the IPC standards, the limits that my customers have to deal with are often set by the end users or OEMs who are purchasing the assembled printed circuit boards from them. And sometimes the limits could be as low as 10 or 15% void area for a certain component that is known to have trouble with voiding. And so my customers often face the challenge of having to reduce voiding below their limits that are imposed on them. Here are some of the root causes for voiding. The number one root cause that we like to point the finger at is gas bubble entrapment. And gas bubble entrapment can be influenced by the flux in the solder paste, the solder alloy, the solder powder size, the stencil design, the reflow profile, the board design, the pad layout, if there are vias in the pad. Lots of different things can contribute to gas bubble entrapment. So one question that I had when doing this work was, how long does it take for gas bubbles to leave the molten solder? So I did a really simple test on a hot plate to show just some differences in the different alloys and how long they hang on to gas bubbles. For example, here's a picture of about 20 grams of solder paste in an aluminum dish on a hot plate. And when it starts to heat, you can see some gas bubbles are starting to come out of that solder paste. Then as you continue to heat, then the gas starts evaporating pretty liberally out of here. Would be solvents and the more volatile materials in the solder paste flux. And then when it reaches this stage where you see some of the solder alloys going liquid around the perimeter, there's a lot of gas coming out of the middle of the solder. And then at this stage where all the solder is molten, there's still a lot of gas trapped within that solder joint, if you will. And it takes time for this to fully coalesce and make a smooth, shiny looking solder deposit, releasing all of the gas. So I was curious about how long this takes for the different alloys, and I've got some data on that. So another major root cause for voiding is the wetting or spreadability of the solder paste. And that is contributed to by the stencil design, the flux, the alloy, the surface finish on the PCB and the component, the reflow profile, and so forth. And so the ability of the solder paste to wet and spread and flow directly influences its ability to drive voids out of the solder joint. For example, on QFN thermal pads, we often design the stencil with a web in the thermal pad. And so the web is a gap in the printed solder paste, as you can see here. So the solder paste bricks are here in dark gray, and then the enig finish here is the web width between those bricks. And then after reflow, without a component on it, it looks like this, where you've got fairly tall mounds of solder where the bricks were printed, but it's just a very thin layer of solder that didn't level out completely in between the bricks. So the web width influences this. So one question we had is, what would happen if we varied the web width, and how does that help or make it more difficult for the solder to completely flow and fill in that gap? And the next step is, how does that contribute to voiding? So in prior work, we tested different window pane designs versus other types of designs like a 5-dot pattern and diagonal stripe patterns. We found that window pane designs could be optimized to minimize voiding in QFN thermal pad solder joints. Lead-free alloys definitely showed different voiding behavior in past studies, although we never looked at the impact of alloy specifically, so that's why we were doing this now. Increasing the area of printed solder paste coverage on thermal pads definitely minimized voiding for a variety of BTCs. I think with a higher mass of solder paste present, it's more able to push gas bubbles out of the solder joint and probably more able to flow and wet to fill in all the gaps. Increasing the stencil thickness had a similar effect as increasing the area of coverage. So if you have the ability to use a higher stencil thickness, again, there's more mass of solder paste in that solder joint. And then we did a test where we changed the IRO pad volume, which helped to decrease voiding specifically for QFNs. Reflow profiles were varied in past work, and they definitely altered voiding behavior. The reflow profiles had different effects depending on what solder paste and alloy we were talking about. So here's how we set up the experiment to measure the impact of solder alloy on voids in solder joints. First of all, we started with 5 different solder alloys, and they were all made into solder paste with the same no-clean lead-free solder paste flux. So we went ahead and used tin lead initially just as a baseline to see how it would compare to the lead-free alloys. Then we ran SAC 305 as the standard lead-free alloy. And then we compared that to S100CV, which is a tin bismuth copper nickel alloy that does not contain silver. And then we also ran LFC2, which is a high reliability alloy with 3.5 silver, 3% bismuth, and 1 copper. And then we ran a low melting alloy called TempSafe B37, which has 37% bismuth with some additives in a tin matrix. So these all have different melting ranges. The middle 3 are fairly close in melting range. They're all kind of in that SAC ballpark. LFC2 is the lowest out of those 3 with a 208 to 213 melting range. And then the overall lowest melting range is this TempSafe B37 from 139 to 174. These were all made, by the way, with type 4 solder powder. This is the test board that we used for the experiment. So the main thing that we were looking for here is voiding on these QFN thermal pads. So these are QFN 68s that have a 10 millimeter body size and an 8.3 millimeter thermal pad. Here are the 4 different stencil designs that we used for this experiment. We started with a 20 mil wide web, which is the standard web width for this design. And then we reduced that to 15 and 10 mil wide webs, and then we also increased it to a 25 mil wide web. The individual window pane bricks were held to the same area, so the area of coverage was held at 65%. And the stencil was 5 mils thick. Here's how we measure general solder paste performance with the test board that I showed. So there's a wetting pattern on that test board where we print 15 bricks of solder paste down parallel lines. The spacing changes from 0.1 millimeter in the center to 0.4 millimeters on the outside edge. And then after reflow, you can see the solder melts together and forms some smooth deposits, especially in the center where the spacing is tighter. But as you go to the outside edges where the gaps are wider, you can see breaks in the line. So we can count up the number of breaks in the line and then from that calculate a wetting or spread percentage based on the total possible number of breaks that could be filled in. Solder balling pattern looks like this. It's a series of 20 mil diameter pads that are separated by different distances, and then we print solder paste onto the solder mask in a fairly large area. The solder paste is overprinted from 500% to 1250%. And then after reflow, the solder pulls into the central sphere and it's surrounded by a pretty big flux pool, and we look for solder balling in the flux pool around these in this pattern. And so we can rank solder balling performance based on the different areas of overprint that we see here. The graping pattern looks like this. So graping is measured through 4 different types of pads. So we've got circles and squares, non-solder mask defined and solder mask defined pads, and they vary in size from 7 to 12 mils pad size, and also the solder paste deposits are those same sizes. The area ratios on the stencil are actually very small. The area ratios range from 0.35 to 0.60 area ratio. So well below IPC standard for area ratios, and it's the smallest deposits on this pattern that usually show graping, and the graping would look like these 2 yellow circled deposits. So we can count up the total number of deposits that show graping and divide by the total possible to calculate a graping percentage. So we tested 5 different alloys in this no clean lead-free solder paste: tin lead, SAC305, S100CV, LFC2, and then this TempSafe B37 alloy. We used 4 stencil web widths, 10 through 25 mils. We ran everything through a SAC305 ramp to spike profile, which looks like this, and the stats on that profile I'll show on the next slide. And we ran a total of 20 combinations of tests. So we ran 5 printed circuit boards per combo. There's 4 QFNs placed per PCB. So we took 20 void measurements per combination. And then we ran an extra 2 combos just to compare reflow profiles. Here's the print parameters that we used for this solder paste. These are all very standard. Here are the measured reflow profile parameters. Again, we use the SAC305 ramp to spike profile for all the comparisons. The time above liquidus was 57 to 59 seconds above 220C. The peak temp was about 241 to 244C. And then we ran 2 iterations just for comparative purposes. I ran the tin lead solder paste in a tin lead profile to compare it to the SAC305 profile. And then I did the same with the tin bismuth solder paste. I ran it in a standard tin bismuth profile to compare to the SAC305 profile. The major difference here is the time above liquidus is a little bit longer for the tin lead and even a little longer still for the tin bismuth, but the peak temps are much different. So 241 to 244 for SAC305, and that was dropped down to 208 to 210 for the tin lead solder paste, and then 200 to 203 for the tin bismuth solder paste. Here are the results for general reflow performance. So this chart shows all of the wetting, solder balling, and graping data. And I've got a performance metric on the y-axis. So wetting is the blue bars, solder balling is the green bar in the middle, graping is the purple bar on the right. I realize these colors are pretty close together, and I apologize if you're colorblind and you can't distinguish between these. Just know that wetting is the first one, solder balling is the middle, and graping is the right-hand bar. So higher performance is better. So 100% is ideal. Tin lead solder obviously had the best performance out of all of these. It had 100% on all three of these categories of wetting, solder balling, and graping. And then the SM100CV alloy had the best lead-free wetting, so it's got a 96 rating, while all the others are lower than that. SAC305 was a 76 for comparison. And then TempSafe B37 had the overall solder balling and graping best performance and also pretty good wetting. So TempSafe B37 did pretty well overall in terms of the lead-free alloys. Here are pictures of the printed circuit boards without components placed on them. So I ran one board for each combination, and I took pictures of the QFNs just to show you what happens with the solder alloy and how well spread it is, or if there's gaps in the bricks, like you can see here on the SAC305. So overall, the tin lead and the low melting tin bismuth both fully spread and wetted on all the web widths. So it didn't matter, 10 mil web at the top down to 25 mil web at the bottom. These are smooth. So there are no web widths visible in this reflood deposit. Whereas SAC305 shows web widths and overall was the worst because it had the most distinguished bricks still left that didn't smooth out. SM100CV and LFC2 are in the middle. They had moderate performance in this evaluation of wetting and spread. Here are the voiding results. This is voiding broken out by solder alloy. Each box plot represents all the web widths combined into each alloy. So you've got alloys across the x-axis and voiding percentage on the y-axis. And then we ran a Tukey-Kramer statistical analysis test and generated a connecting letters report. So if the letter codes are different in this connecting letters report, then the data sets are significantly different. And that was done with a 95% confidence level. So you can see that overall SM100CV had the highest voiding, and it was statistically higher than all the other alloys. The overall lowest voiding was with tin lead and the tin bismuth alloy, which are shown here in these box plots, and they were significantly lower than the other alloys. And I wanted to correlate this to this gas escape time that I was talking about earlier. So I did put 20 grams of solder paste in an aluminum dish, and as soon as I put it on the hot plate, I started a timer, and then I looked at the amount of time it took from beginning the heat to when the last gas bubble escaped out of this solder deposit. Here's the times. So you've got, these are ranked from lowest to highest, quickest to longest. So the low melting tin bismuth had 100-second gas bubble escape time, followed by tin lead at 160. Then SAC305 was in the middle at about 270. LFC2 was close to that at 300. And then the S100CV had by far the longest gas escape time of 450. And then just putting the mean void area for each one of those alloys on this chart, just for comparison, they're roughly ranked from lowest void area to highest. They kind of correlate to the gas bubble escape time. So when I saw this data, I said, well, I should run a correlation. Let's see if I can put a line through this data. So here's the plot of void area against gas escape time, and it's roughly linear. So, and it's got a R-squared value of 0.94, which is pretty good. TempSafe B37, lowest gas escape time, also had the lowest overall void area. And then in the middle, the LFC2 had a lower void area than the SAC305, but it had a slightly longer gas escape time. So that's the one anomaly on this data set that's farther off the line than the others. And then the highest overall was SM100CV, and of course that had the highest void area and the highest gas escape time. So this is kind of an interesting test where maybe this is a quick and dirty way of trying to evaluate what the voiding potential is for a solder paste just by reflowing it on a hot plate and measuring the gas escape time. At least it can give you that root cause for voiding. It can give you some idea of how long that solder alloy itself is going to hold on to gas bubbles. And that might be related to the composition of the alloy, how the alloy forms intermetallics, if the alloy has a high surface tension. Those things might play a role on how long it holds on to gas bubbles. This is voiding by web width with all the alloys included in each box plot. So we've got web widths on the x-axis ranging from 10 mils up to 25 mils from left to right. and then void area percentage on the y-axis. Looking at this connecting letters report, they all have the same letter codes and the mean void areas are all very similar, so there's no significant difference between these data sets, which means that web width did not change voiding when we include all of the alloys in the data sets. This is voiding broken out by alloy and web width. You've got void area on the y-axis, and then each alloy in each major category here. LFC2, SAC305, then SN100CV, tin lead, and then tin bismuth. And then the different colored box plots are the different web widths. So on the left is the green box plot, that's the 10 mil web width, followed by the 15 mil web width, which is red. The blue box is 20, and then the pink box is 25 mil web width. Overall, you can see the SN100CV has pretty high voiding compared to the other alloys, and then the tin lead and the tin bismuth have overall very low voiding regardless of web width. And at the left side of the chart, the LFC2 and the SAC305, you can see voiding increases with increasing web width. So in general, LFC2 had low overall voiding that increased with web. SAC305 followed the same trend, low to moderate voiding that increased with web width. SN100CV had high overall voiding regardless of web, and then the tin lead and the tin bismuth had low overall voiding regardless of the web. So here's the LFC2 and the SAC305 connecting letters reports from the Tukey-Kramer analysis. So LFC2 definitely shows higher voiding for the higher web widths. Same thing for SAC305, and those results are significant. And then the SN100CV, these letter codes are all the same. And so the voiding was just high overall, regardless of web width for SN100CV. So in that case, the voiding potential or the gas entrapment potential of the CV overcame the influence of stencil design to mitigate voiding for that alloy. And then the 6337 and the TempSafe B37 both had overall really low voiding. And there was some difference in the connecting letters reports, but they're kind of varied. Like 6337 showed slightly higher voiding for the 10 mil web, whereas the tin bismuth alloy showed higher voiding for the 25 mil web, just slightly. But there's not a huge difference there. Overall, the voiding was very low for all those. This is the voiding by profile for the low temp alloys. This is the comparison where I ran one iteration of each of these low melting alloys in their normal profile to compare to the SAC305 profile. So this first chart is for the tin lead solder paste run in both the SAC305 profile on the left and the tin lead profile on the right. And you can see the voiding is significantly higher in the tin lead profile. Now that might be due to the fact that this flux is normally used for lead-free applications, and therefore in a tin lead profile, the volatile materials might not all escape completely before things hit liquidus and then freeze again. Here's that same data for the tin bismuth alloy. The SAC305 profile again is shown on the left, and then the tin bismuth profile is on the right. Same trend is shown here, where the tin bismuth profile gave higher overall voiding for that solder paste and alloy combination. So overall, running both of these solder paste in a SAC305 profile gave lower voiding. Here are conclusions based on this data and some recommendations on how to mitigate voiding in solder joints. Both gas entrapment and pore wetting or spread can increase voiding potential. Alloys that have a higher potential to trap gases or hold on to gases for a longer period of time can increase voiding, as well as alloys that may contribute to pore wetting or spread. Solder alloy in combination with the web width affected voiding in this study. Some of the alloys were impacted by wider webs, which generated higher voiding. The tin lead and the tin bismuth both had low voiding regardless of web. LFC2 had low voiding but increased with web width, as did the SAC305 alloy. And the SN100CV alloy had high voiding overall, and that did not change regardless of web, so we were unable to influence the voiding potential of that alloy with stencil design. Reflow profile changes influence voiding for the tin lead and the tin bismuth alloys. And in future work, we might run additional profiles to see if that can have an impact on this voiding potential. Here's some recommendations on how to fill the void. Choose solder alloys with low voiding potential if you have the ability to change the alloy. Of course, we realize that you may not have that ability. The alloy might be dictated based on the assembly you're building or by your customer. But if you do have the ability, or if a customer dictates a different alloy and you're running multiple alloys on different products, just realize that the alloy can have an impact on voiding. And if you're struggling with voiding limits, if you have the ability to change the alloy, that might be one route to take. Recommend minimizing web width in your stencil designs. The smaller the webs had an impact on voiding for some of these alloys, and we were able to reduce voiding by minimizing web width for a couple of the alloys. I also recommend that you tune the reflow profile for the solder paste in the alloy. So that's a good, easy place to start. If you're looking to minimize voiding, the reflow profile can be changed, as you know, pretty quickly. Like within an hour, you could have a new profile running and you could check and see if it has an impact. So your solder paste supplier should be able to recommend what changes to make for that solder paste and alloy combination in order to mitigate voiding. Thank you for your time and your attention. Again, if you have any questions, feel free to email me or call us at our main phone number. Have a great day.